Now, next quiz, I want you to fill in the probability of having cancer, given that we just received a positive test. And the correct answer is 0.043. So even though I received a positive test, my probability of having cancer is just 4.3%, which is not very much, given that the test itself was quite sensitive. It really gives me a 0.8 chance of giving a negative result if I don't have cancer. It even gives me a 0.9 chance of detecting cancer given that I have cancer. Now, how come this value is so small? Well, let's just put all the cases together. We already know that we received a positive test. Therefore, this entry over here and this entry over here are relevant. Now, the chance of having a positive test and having cancer is 0.009. Well, I might, when I receive a positive test, have cancer or not cancer. Let me just normalize by these two possible causes for the positive test, which is 0.009 plus 0.198. When I work these two things together, I get 0.009 over 0.207, which is approximately 0.043. Now, the interesting thing in this equation is that the chances of having seen a positive test result in the absence of cancers are still much, much higher than the chance of seeing a positive result in the presence of cancer. And that's because our prior for cancer is so small in the population that it's just very unlikely to have cancer. So the additional information of a positive test only raised my posterior probability to 0.043. So we just learned about what's probably the most important piece of math for this class in statistics, called Bayes' rule. It's invented by Reverend Thomas Bayes, who was a British mathematician and a Presbyterian minister in the 18th century. Bayes' rule is usually stated as follows: P of A given B, where B is the evidence and A is the variable we care about, is P of B given A times P of A over P of B. This expression is called the likelihood, this is called the prior, and this is called the marginal likelihood. The expression over here is called the posterior. The interesting thing here is the way the probabilities are reverted. Say we have evidence B, we know about B, but we really care about the variable A. So for example, B is a test result. We don't care about the test result as much as we care about the fact whether we have cancer or not. This diagnostic reasoning, which is from evidence to its causes, is turned upside down by Bayes' rule into a causal reasoning, which is, given hypothetically we knew the cause, what would be the probability of the evidence we just observed? But to correct for this inversion, we have to multiply by the prior of the cause to be the case in the first place, in this case having cancer or not, and divide it by the probability of the evidence, P of B, which often is expanded using the theorem of total probability as follows. The probability of B is the sum over all probabilities of B conditioned on A, lower caps A, times the probability of A equals lower caps A. This is total probability as we already encountered it. So let's apply this to the cancer case and say we really care about whether we have cancer, which is our cause, conditioned on the evidence that is the result of this hidden cause. In this case, a positive test result. Let's just plug in the numbers. Our likelihood is the probability of seeing a positive test result given that we have cancer, multiplied by the prior probability of having cancer, over probability of the positive test result. And that is, according to the tables we looked at before, 0.9 times a prior of 0.01 over, now we're going to expand this by over here, according to total probability, which gives us 0.9 times 0.01 That's the probability of plus given that we do have cancer. So probability of plus given that we don't have cancer is 0.2, but the prior here is 0.99. So if we plug in the numbers we know about, we get 0.009 over 0.009 plus 0.198. That is approximately 0.0434, which is the number we saw before. So we want to draw a Bayes rule. Graphically, we have a situation where we have an internal variable A, like whether or not we have cancer, but we can't sense A. Instead, we have a second variable called B, which is our test, and B is observable, but A isn't. This is a classical example of a Bayes network. The Bayes network is composed of two variables, A and B. We know the prior probability for A, and we know the conditional. A causes B, whether or not we have cancer, causes the test result to be positive or not, although with some randomness involved. So we know about the probability of B given the different values for A. And what we care about in this specific instance is called diagnostic reasoning, which is the inverse of the causal reasoning. Probability of A given B, or similarly, probability of A given not B. This is our very first Bayes network, and the graphical representation of drawing two variables, A and B, connected with an arc that goes from A to B, is the graphical representation of a distribution of two variables that are specified in the structure over here, which has a prior probability and has a conditional probability as shown over here. Now I do have a quick quiz for you. How many parameters does it take to specify the entire joint probability between A and B, or differently, the entire Bayes network? I'm not looking for structural parameters that relate to the graph over here. I'm just looking for the numerical parameters of the underlying probabilities. And the answer is 3. It takes one parameter to specify P of A, from which we can derive P of not A. It takes two parameters to specify P of B given A and P given not A, from which we can derive P not B given A and P of not B given not A. So it's a total of 3 parameters for this Bayes network.